Hi everyone, welcome to this webinar. The title of webinar is 3D geometry creation and modeling in Slide3 software. My name is Sina Javankoshtel. I'm a product manager of Slide3 software, and I would be happy to present in this webinar. We are Rocscience. We are the world leader in developing 2D and 3D software for civil, mining, and geotechnical engineering. For over 25 years, we have built geotechnical tools used by over 10,000 users around the world. And we are dedicated to delivering industry-leading software programs, exceptional customer service, and unparalleled technical expertise. And engineers can rely on our services. We have a webinar series, a Slide3 webinar series. Today is part one, which, as I mentioned, I'm going to talk about 3D geometry creation and modeling. Okay. Part two is going to be 2D and 3D LEM modeling. And part three is going to be a statistics and back analysis in slide 2 and slide 3. So these three webinars, we have prepared different types of materials to show you different features of the software. In 2D and 3D, the focus is on a slide 3, but obviously slide 2 and slide 3, they are integrated, and we talk about the slide 2 as well. And in these three webinars, we are trying to show the new features that we have developed recently as well. So probably at the end of each webinar, we show a couple of new features that we have in the software as well. So let's get started with the first one. In this webinar, I'm going to talk about geometry creation and repair in slide 3 and RS3. The reason that I put RS3 here, which is our 3D finite element software, is a Slide 3 and RS3, they share exactly the same geometry tools. So if you want to create a geometry or a repair, it doesn't matter if you do it in a Slide 3 or you do it in RS3. You can do it in both software, and they can be transferred between these two. So I'm going to talk about it first, and then I'll go and talk about slope stability analysis using Slide 3 software. Okay, let's start with geometry cleanup and model creation. As 2D users, or at least we used to be 2D users, most of us, we are dealing with lines in 2D analysis. So if you want to make a geometry in 2D, you just use polylines. So we are very comfortable with these polylines. So as a first-time user of any 3D software, the first thing that comes to your mind is, okay, I have some lines and I want to make a 3D geometry. So that's why I'll start with this one. So to make a 3D geometry, the easiest way of doing it is just to use lines and then extrude these lines. I use different tools that I'll show later to make your geometry. Or for a lot of civil applications, mostly we deal with typical geometries like boxes or spheres or planes. So these are 3D primitives that they are built in the software. So that's another way of creating 3D geometry. As I mentioned, when you have lines, you can make them surfaces or volumes. The thing is, you have to know that if you have a 3D model, if you want to do a 3D analysis, the software packages, they only work on volumes. Surfaces come for like groundwater analysis, like water table or anisotropic surface or weak layers. But the software only focus on the volume. So the goal is to change everything to volume. So if it's polyline, if it's a surface, so it has to be a volume at the end. So these are some of the tools that we use to extrude, sweep your lines and surfaces to make them volumes. When you have a raw volume, you can define different planes to cut your volume, to look at to create your geology and make your 3D geometry. Or we have the borehole manager. So if you have borehole data, you can bring it to the software, and similar to this example, when you have a raw geometry and you have your borehole data, the software is going to create a layered geometry for you. So this is another way of making a 3D model. Sometimes the type of data that you have is in terms of like point clouds. And when you have point clouds, you can just use them to make a surface and use the surface to make a volume. So this is another feature that you can make a geometry. Other one is elevation contour. So if you have your geometry as contours like this, there is a feature in the software that you can make these contours and change them to surfaces. So that's the other thing that you can do. Or we have a general import. Basically, any geological, civil, and mining software, any geometry that you export from them, you can import it to our software. So we accept DXF files from AutoCAD, we accept OBJ, STL, different types of geometry. So you can directly import them to our software. When you do that, this import geometry dialog comes up, and you can bring everything into the software, or you can select whatever you want as part of the geometry to import it to the software. However, since you are bringing geometries from other tools, you need to do some sort of post-processing or cleanup for your geometry. There are two ways of doing it. I'll explain them, and I'll mention the difference between them after. They are identical, but there is a slight difference between them. So basically, what you can do is go to the post-processing step. And in the post-processing step, we have simplified triangulations and find and repair defects. So you can repair your geometry here and simplify it here. Or you don't have to do, this is optional, you don't have to do that. You can just click on done and bring everything in the software and repair it there. It's up to you, but I'll explain the differences. So let's look at, I'll explain the repair tools that we have, and then I'll go back to this post-processing section. We have two different types of repair tools. One is to repair the defects of the geometry, including holes or other defects. And the other tools that they are part of the repair, that they are surface triangulation tools. The repair tools is the left one. So basically, there are 5 different issues that we detect in the geometry. And it doesn't mean that your geometry is bad. As I mentioned, the criteria that our software has to create the geometries might be different. So we fix these first, and then you can create your own geometry. There are a lot of third-party software packages, but the advantage of Slide3 and RS3 is that you can do all the repairs in one single software, which is very easy. And for example, for this one, we only have 19 near degenerated. Near degenerated and near folding, they are minor defects. So the software allows you to create the geometry even if you have these kind of defects. But holes, self-intersection, and non-manifold, they are type of defects that you have to repair them. Otherwise, the software does not allow you to create your geometry. So that's one type of fix. The other type, as I mentioned, is surface triangulation tools. And one of them is retriangulate, which is the most used option. So let's see what is this surface triangulation option. So mathematically, if you want to make a create a surface in 3D or in 3D world or a volume, you need to use some kind of mesh, which is called surface mesh, and they are triangulations. They are triangles. So these triangles are used to create your volume. Uh, they must have some features to be good, to be able to create a geometry. First of all, they should be uniform, which is this one is not. You can see these triangles compared to the triangles on the volume. And they should be almost the same size. In terms of size, they should be uniform as well. We have these retriangulation tools in the software to fix this. So that's another type of repair that you can apply to your geometry. So this is retriangulated in the software, and you can see that they are uniform, same size. And look at this side, because I have other examples, I want you to focus on those as well. So look at this side and see how smooth your geometry is. We have another option, which is like high resolution, low resolution. The resolution in limit equilibrium is a little bit less important than the finite element. Here, we are not talking about limit equilibrium finite element. I just wanted to mention in the geometry part. So basically, in the finite element analysis, the volumetric mesh is a function of this surface mesh. So if this surface mesh is bad or too dense, it's going to affect your volumetric mesh, which is very important in the finite element analysis. But in the limit equilibrium analysis, as long as this one is fine enough to that you are able to create a geometry and your geometry is not problematic, it represents your topography, for example, that's fine because it's limit equilibrium. It's not that complicated as long as you are able to create your geometry. Like this one is not good, not in a limit equilibrium, not in finite element, because it's too dense and the size of your file is gonna be huge. And this one is not good too. Look at this side, as I mentioned at the beginning, the face of this tunnel. You can see that it's not as smooth that it was in the first retriangulated picture that I showed you. So it shouldn't be this coarse either. So it should be fine enough. And if you use the default of the software, it's always 99% of the time it's good. These very fine retriangulations has its own specific application that's out of the scope of this presentation. Let's look at another example. I want to show you the difference between modifying your surface, cleaning up the surface in the post-processing section or in the software. So let's say we brought this one in the post-processing section. The first question that a lot of people ask is, what is the typical number of triangulations that we should use? There is no pretty common like for fine 10,000, for coarse 5,000, but I've seen surfaces with 3 million triangulations and huge surfaces for civil applications coming from AutoCAD. And some people think that if it's too fine, it's better. No, it's not. So as long as it's fine enough to represent your up and downs in the surface, that's enough. But here we have 3,000. Even 3,000 for this one is enough. It meets our criteria, but you can change it and even simplify it a little bit more. It doesn't change your geometry. So we picked custom number of 200. But if you have 3 million triangulations, it's not going to go down to 10,000. Sometimes 50,000 is enough. Sometimes 100,000 is enough. So it depends really on your geometry. After refining this one, you can find the defects and you can see, okay, we only have 4 near degenerated, 1 click repair, and it's repaired. So that easy. Now, what's the difference between this one and the one you can see that there are 2 exactly the same surfaces. One without arrow beside it is repaired in the post-processing section. One is repaired in the software. There is an arrow beside it. So that's the difference. If you do the repair in the post-processing, no history is going to be left. So it's going to be a fresh surface being imported to the software. So you can't see the original surface. But if you bring the surface in the software and do the repair, this arrow shows the history. So you have access to the original surface. It's good and bad. Good because you have access to original, bad because If your original is too dense and very heavy, your final file is gonna stay heavy. So you have to be careful. So, but at the end of the day, the output is gonna be the same. So the same surface, the same fixes, everything is the same. As I mentioned, we deal with volumes. So if you have a volume in your geometry, the software is going to focus on that one. However, we define a concept which is a reference volume, and we call it external. So if there is trash bin in front of your entity, it means that it's not part of your external geometry, and the software is going to ignore it. So it has to have a lock in front of it, which I'll show you in the example, to make sure that the software is going to do the computation on it. There are different ways of making external geometry using a box, external from surface, different options that I'll show you a few of them later in the examples. So we imported the surface, make it volume, make it external. And now we want to see how Slide3 does the limit equilibrium analysis for that volume. So here's the difference between 2D and 3D analysis. 3D analysis, the most important part, in my opinion, is how you make the geometry and how good is your geometry. And it requires some expertise. But the rest, the concepts, they are mostly the same with 2D. And in the next release of a Slide2 and a Slide3, which we're going to talk about it in the next webinar next month, um, it's a very high integration. We worked on it a lot, and it's more than 95% integrated. So you can match 2D and 3D features in terms of features and methods. Okay, this is a Slide3. We have three locked view, different axes, and one rotate or 3D view, which is on the top right of the software. So if you want to make a model in a Slide3, the first step is to make the geometry. After making the geometry, if you have loading, if you have support, if you have groundwater, you can apply those. But there are four things actually, that you have to define properly. Material strength, based on your data, analysis methods, search methods, and search limits, which I'll go through them one by one. So geometry part, I explained, we have different ways of doing geometry. This is a full 3D software. It's not just extruded geometry. Extrusion is the easiest way of making a 3D geometry, and I'll show you two examples today. One is extruded and one is making a full 3D geometry to show you the differences. And extrusion has its own advantages, especially when you have different boundary conditions, but you have all the options. You can make your geometry if you want to extrude or you want to import geometry. These are four limit equilibrium methods that we have in Slide3: Bishop, Bienbout, Spencer, and GLE. Spencer and GLE are the most rigorous ones. And these are the most usable methods that we brought from Slide2 to Slide3. We have four different types of shapes for critical slip surface, which is very important in 3D. Spherical, ellipsoidal, multiplanar, and wedge. Spherical is equivalent to the circular search in 2D, and ellipsoidal is kind of non-circular search. And the search method in 3D is very important because it has to go all over your 3D geometry to find the critical slip surface. The traditional methods that we don't normally use is grid search and auto refine. And the default methods in the software, they are materialistic methods, which are very strong methods in 2D and 3D. We have it in both Slide2 and Slide3, including cuckoo search and particle swap. And the slip surface can get any shape using these two methods. On top of these search methods, materialistic search methods, we have our in-house advanced local optimization method, which is called surface altering optimization, which is gonna optimize your critical slip surface even more. So, and that's the key, because in the 3D slope stability analysis, you should find the correct critical slip surface. Otherwise, your slip surface gives you the wrong factor of safety. Supports, we have different types of supports. In slide 3, we had a webinar more than a month ago about support and loading, so about supports in slide 3, and with the focus of RSpile, which is a new feature in slide 3. And I think it's available on YouTube. You can watch it on YouTube if you are interested. Loading, we have point load, distributed load, and seismic load, and you can apply your loads at different orientations. And groundwater definitions, we have water table or water surface, for water pressure grid, and RU coefficient. You have the option of doing seepage analysis in RS3, and as I mentioned, the advantage of RS3 and Slide 3 sharing the same geometry is that you can do the seepage analysis in RS3 and bring the pore water pressure as grids in Slide 3. So I'll show you one example specifically for this feature today. Material models, we have different types of material models, same as Slide 2, including the general ones like more Coulomb, generals anisotropic, and a lot of anisotropic models as well. And you can see at the end we have block model. I'll explain the block model in the new feature section, which is a new feature that we have in the slide. Tension cracks, you can define tension cracks in slide 3 using surface option or tension crack by location. This is one of my favorite parts, is slide 2, a slide 3 integration. In a slide 3 software, we have a separate section for a slide 2. So you don't have to create a section, export it, and run it in slide 2. It happens in slide 3 software. So we have an engine built in slide 3, a slide 3 engine built in slide 3. And you can even open the slide 2 modeler, make your changes, and refresh the results. And as I mentioned, the next release, our focus is on this feature and make it much more strong. So you can take as many sections as you want in your 3D model, run the 2D engine, and look at the results and compare with the 3D results, which is very important. In terms of results integration, we have different options. You can look at the global minimum. You can look at all surfaces in your 3D model. You can look at safety map. Safety map is based on the different values of factor of safety at different locations. And this is the difference between how many slip surfaces we use. I typically use the default of the software, but if you want to focus more on a specific region, you can define the focus search for that region, or increase the number of surfaces for search. This is column viewer, similar to the slide to a slice viewer that we have. So you can look at different values for each slice. Here you can look at different values for each column. And this is for the critical slip surface, and you can see different materials in that slip surface. And these are all the parameters that you can have to do your hand calculations for the limit equilibrium analysis. We have contour options, so you can look at different contours for your critical slip surface, including cohesion, friction angle, all different contours. We have also the monitoring data as well. So you have the option to import your monitoring radar data. We have different companies, and we are adding different companies as well, and compare it with the numerical analysis. So you can compare the results of slide 3 with the radar data that you have and see if they make sense or not. What's new in the software? One of the cool, maybe the coolest feature that we have is multimodal optimization. So traditionally, limit equilibrium software packages only give one critical slip surface, which we call it UMO. unimodal optimization. So for this open pit, which is kind of symmetrical, you see that, okay, there is a slip surface here. And if you can expect there is a lower factor of safety on the other side of the pit as well. So to get that one, you have to define a focus search, a search limit for that specific region to give you the critical slip surface. But we develop an algorithm in a slide 3 using particle swarm optimization, which is one of the materialistic methods, that gives you a couple of critical slip surface. So it not only gives you the global minimum, it's going to give you the local minima as well for your model. So you can see that for this specific model, we got 3. Not only this one, we got another one very close to that value, and we have 1.11 on the other side of the model as well. So you just run multimodal and you get all this. We added probabilistic analysis before pandemic. We have a method called stochastic response surface method, which is one of the advanced method of doing probabilistic analysis. We explained this in our third webinar. But if you require 1000 simulation using Monte Carlo simulation or Latin hypercube simulation, you need only like 30 using response surface method, which is very important for the 3D modeling. For 3D modeling, you can't do thousands of simulations because it's time consuming. You can do back analysis using this probabilistic feature as well, which we'll explain in the third webinar. Block model in a slide 3. So as I mentioned, you can import a slide 2 model in a slide 3 to make a 3D model. You can import surfaces and volumes. You can use the CAD tools in the software to make the geometry. And the last one, which is the new one, is you can import block models. So for mining applications, you may have block models like this, X, Y, Z, and value for the blocks. And you can import them as a new material model, which is called block model. And the software makes a geometry like this for you, which is a block-based geometry. So you can make your changes and you can look at the failure surface similar to the regular geometries that we have, which is a very cool feature as well. So let's go to our examples. I have 30 minutes for 2 examples. A little bit less because there are questions that I want to explain. The first example is a levy with relief wells. I'll start with the finite element software. This is RS3 software. I'll show you this one first because I want to explain what I did, and then we go to slide 3. So I'll go to the 2D view first to explain the problem. So this is our levy, and this is our retaining wall, and we have ponded water behind. So you can do the 2D analysis, but the thing is we have relief wells here, and when you define relief wells in 2D, the assumption is that the length of the relief wells, they are infinity. So it's equal to infinity. In the next webinar, which we compare 2D and 3D, I'll talk about differences between 2D and 3D a lot, but I am justifying the reason that we use the 3D analysis for this one. So, but in 3D, you have the advantage of defining different spacings for your relief wells. So if I go to the 3D model and I just show you the sections that we have in this model, I will hide the materials, and we have 2 contours. Yeah. So if I show you these 2D contours, you can see that these relief wells are defined at different spacings. It's not infinity. And to make it happen, you can't do the 2D analysis. And we wanted to define these boundary conditions in our 3D model. So that's why we did a seepage analysis in RS3, and we are taking the results of the seepage analysis to Slide 3. So if we look at these wells, there is a relief well option, Victorian or relief well option in RS3. So you can see that these relief wells are defined at the spacing of 50 meters or 50 feet. So that's one boundary condition. We have ponded water, and also we have a total head on this side. So the advantage of relief wells is to reduce the pore water pressure on this side because they have lower head compared to this side of the model. So we did the seepage analysis, and this is the results of seepage analysis. This is the exterior contour. You can see that the head here is 115, and it goes down to 106 to this side. So this is pore water pressure calculation using the seepage analysis. What you can do, you can just export this pore water pressure to a Slide3. So we did the seepage analysis in RS3, and now we export the pore water pressure to a Slide3. So you can define different options, different spacing for your relief well, do the analysis, export pore water pressure, and import it to a Slide3. If I want to show you the Slide3 models, so I did two spacings. One is 200 meters for relief wells, and one for 50 meters, 50 feet, sorry, for relief wells. And these are the pore water pressure grids that I imported from RS3 to Slide3. So I did the seepage analysis and I imported the pore water pressure grids. The other thing that you can see here is, as I mentioned, these are different geometry pieces that I have, and they have a lock in front of them. So it means that they are part of my external geometry. Before we discuss the results, we go to the project settings. We have a Spencer method check. We only checked one method for this one. And if we go to the surface options, we have cuckoo search, surface altering optimization. These are meta-heuristic and local optimization methods that I mentioned. And yeah, then we started, we ran this model in advance, and we got the factor of safety for, let's go to 200, 1.37 when the spacing is 200 feet. And when we reduce the spacing, which is closer to the infinite case, the factor of safety goes up. So it's 1.55, and this is our critical slip surface. Now, just to quickly confirm the results of limit equilibrium, which we always do, we compare the results of limit equilibrium and finite element analysis. You can see that critical SRF in the finite element, 3D finite element, is 1.59. This is for 50 feet spacing, which is very close to the results of limit equilibrium analysis. To show you some other features that we have, for example, safety map. You can see that safety map shows that this is the region of critical factor of safety, and we have other places that they are safer. You can look at the contours for the critical slip surface. You can look at pore water pressure because we have pressure grids, and you can see that this is the pore water pressure that we have in our critical slip surface. You can look at base cohesion. Base cohesion means that what material, it shows that what material your critical slip surface is going in. So you can see that we have two values. So basically, if we go to the material section, we have like 4 different materials, but these two values are 30 and 50. So 30 is for the levy and 50 is for the fat clay number 2. So it shows what material we are going through. You can look at the column viewer. So when we click on the column viewer, it goes and show the values for our columns. So it's, I think because of the pore water pressure, it's thinking. I can show you in other models. This might take a while. So These are different features that we have for that C page, bringing C page results into the slide 3 results. Okay, I will discuss this model in the next webinar as well, because we want to look at the 2D analysis, the differences between the results of 2D and 3D. Next example, if I go back to the presentation, is this one. So we want to look at the slope stability of open pit. Before doing that, actually, there is a question about the course, slide 3 course training. Um, we are going to have a course starting tomorrow in Los Angeles for 2 days. So if you are interested in training and courses, just let us know, and we would be happy to provide it for you. Okay, let's go to our next example, which is a slope establishment of open pit mine. In this example, what I'll do, I'm gonna start making the model from scratch, and to show you how to clean up the geometry, how to make the external volumes, and all these sort of things. So I have a model, actually a couple of entities. Um, this is the initial file. So we have a topographic surface, which is called topo, and we have like 4 different surfaces to make your the geology of the model. These ones are clean, so I cleaned them in advance, and they were okay. But this topographic surface, obviously, the first thing that you always do is if you want to repair your geometry, you come to geometry, repair tools, and click on repair to see the issues that your geometry might have. But as I mentioned, to clean up a geometry is a combination of surface triangulation tools that we have and the repair tools that we have. So here you can see that 269 near degenerated issues, near folding issues, self-intersection issues, and non-manifold. So I can repair it here. I don't know what happens, but these are not issues that the software can't clean. I want to show you some alternative, because it's not just one way of cleaning. You can combine different options to make a nice model. So for this one, I looked at this. Let's go back one more time. I'll show you something. If you look at here, we have 14, I believe, 14 non-manifold problems for this geometry. So I click on this one, go to geometry, and we have an option for it on group non-manifold. So non-manifold sometimes mean that there are some teeny tiny pieces connected to your geometry that they are not part of your geometry, and you can discard them. So this ungroup non-manifold means that you can discard those pieces and separate them from your original geometry. So I just click on ungroup non-manifold, and we see what happens here. So this is my original geometry, and these are those pieces that you can't even see here. They are very teeny tiny and connected to your original geometry and causing issues. So you can just, we have 2 roles, geology and construction. Construction means that the software is going to ignore them. And to remove a piece of geometry, you should change them to construction and go to geometry, discard construction geometry, and it's going to be removed from your geometry. If I go back to the repair tools, you can see that I think those non-manifolds, most of them should be gone, if not all of them. Yeah, all of them are gone. But removing them caused 3 holes in the geometry, which is interesting. So for now, I just click on repair and see what happens. We have a lot of near degenerated, so it might take a few seconds. While this is repairing the geometry, and you can see that the first step is retriangulation. So the retriangulation option is the first step that we always do, even in the repair tool that we have, to make the triangulation nice and then start repairing the geometry. So I'm trying to go through the question and see if there is anything interesting that I can explain. I will explain as much as I can at the end. One question is, are Slide 3 or RS3 models run in parallel mode? Yes, all of our software packages, they are a parallel process. And because if you don't run 3D models in parallel, it's going to take a long time. And this is one of the things that Rocscience is strong at. Like we run our software in parallel mode to make it much faster. So yes, the answer to that question. So with one click of repair, my geometry is repaired. It's not magic. For a lot of geometries like that, the software can easily find the issues and repair them. So this one is fixed. So when the geometry is repaired, and as I mentioned, this all goes to your history. So this is my original. This is after discarding those non-manifolds, and this one is after the repair. So you can see the history. Now we use this geometry, and as I mentioned, you have to make it a volume. So I changed the surface to a volume using this option, create external from surface. You can create, since it is kind of a square, you can make a box around it and then cut the box with this surface and make an external. That's possible. There are different ways, but this one, since this is a topographic surface, it's easier. I just use this surface and create an external using this surface. You can put a depth. I put 160 for the depth and hit OK. And my external geometry is being created. I talked about triangulation. I just wanted to show you for the fun of it. The triangulation after making the external, if you look at, go to View, Show All Edges, you can see that this is the triangulation that this model has. This is surface triangulation. It's not volumetric triangulation that you have in finite element. But it is nice, uniform, and it's ready to go. So the next step is, now I have like these surfaces to make my geology. So what I'll do, there is an option called divide all geometry. What it does, you can see we have one external which has a lock in front of it and a couple of surfaces that they are not part of external. So what's going to happen is, using divide all option, these surfaces, they're going to cut my external volume, make different regions of material, and whatever is not part of external is going to disappear. So these corners of these surfaces that they are not within my external region is going to disappear. But be careful. To be eligible to cut your geometry, the surface has to go through your geometry entirely. So you can see that all these surfaces, they have some extra piece outside of my volume. So they have to cut my volume entirely. So I go to geometry, divide all geometry. I normally use the default options and hit OK. The reason that I'm using default, because these are all being worked on every day, different models, and we come up with the numbers as a default, even for the search methods, that they are good for 90% of the cases, even more. They have more than 90% success. So that's why we recommend those numbers. But if you have a problem, specific problem that does not work with these numbers, feel free, we give you the option to change the numbers. So this is gonna be done soon. When you do the divide all, you cut your external boundary with these surfaces. Most of the times, you have small pieces coming up because these are mathematically intersection between surfaces and volumes, and you have a couple of surfaces at one intersection. So some small pieces may appear that can be part of a bigger piece. So this is part of our geometry cleanup tool. It's actually in the repair tool. So you want a geometry that's clean and as less entities as you want here. So we have so many entities, like some of them are this small, which can be part of a bigger one. To fix this, and again, this might not be a problem in limit equilibrium, but in finite element, because the software is trying to refine the mesh as small as possible to cover these small pieces, it's better to make them part of a bigger piece. So we have an option called collapse small volumes. Here we have one option. You can say how many pieces you want at the end. So I want to say 5 pieces total I want at the end. And it says, okay, so these ones, they're gonna be collapsed and they're gonna be part of a bigger piece. I click on collapse and you only have 5 pieces at the end. Now, if we go to the material menu, I defined 4 different material types. They are all shear normal functions. Uh, so these are defined by shear normal function. We had some lab tests, direct shear tests, so you can define in the Slide3 software. And I want to assign this material to different pieces. You can select the piece, go here and change the material properties, or we have a better tool, which is the 2D tool. You can click on it, and then you have these 5 volumes assign different types of material to it. So just select one from the left, M3. I'm gonna assign it here. M4, M1, M2, and again M4. And hit OK. Geometry is created. I'm gonna make it opaque so you can see that. You can see how nice those surfaces with their shape cut my volume and created a very nice volume like this. So I'm not gonna run these ones. I ran them before. So I'll show you this one is almost ready. The only thing is we have to set the analysis project settings. I'll go with Yambu because it's the fastest one and it gives the lowest value of the factor of safety. And for the surface options, I'll go with particle swarm. For this example, I'll explain why. And you can see that this is one and multiple. This is the MMO multimodal option that I explained that I'll show you some result of it today. So I ran this model before, same model, same type of material, and I got the factor of safety of 1.327. So this is my critical slip surface. We can look at the contours as I mentioned. You can look at the contours of cohesion, and you can always go to contour option, change your ranges, use custom ranges, or change the type of the colors that you want to look at the contours. And it seems that the range is around here, 50. And look at all the slip surfaces that we use to search for this critical slip surface. You can see all the slip surfaces that we have. And what else? You can always make a section cut, a 2D section cut. And the software is gonna cut your volume, the 2D section. I add a section cut. And when I close this one, the section cut is here at the point of this when we cut the model, and this is the critical slip surface. I can hide this one and I can add 2D section cuts to take it to a slide 2. So you can go to plan view, you can rotate this one, and this is at the location of the critical slip surface. You can see that this is the critical slip surface in 2D, and hit OK, and it's gonna come here, and you can run your model. Let me hide the section cut. This is the 2D. And you can run the Slide 2 engine to look at the results of this surface, which I'll do for you because our next presentation is about the difference between 2D and 3D. I'll prefer to do it over there. Now, what I want to do is to go one more step for my initial model. So we created this geometry. What I have, a lot of open pit models is an anisotropic surface. So I would like to add an anisotropic surface, define the anisotropic surface, um, and then define the material for this anisotropic surface and see how the results change. So we click on it, go to material, anisotropic surfaces, add anisotropic surface. So this anisotropic surface is added, but it's not in use. We have to change the material. We go to define material. I would like to change my M4 material, which is currently a shear normal function. I'm going to change it to generalized anisotropic model. We go to edit. Uh, we need to define a base material. Our base material basically is our shear normal that we had for this M4. Can change it to even M4. It's in the material dialog I'll show you. We have deep direction option and we have the surface option. So surface we already added. Material for bedding, we need to define a bedding material, which is defined, and hit OK. So this is our bedding, which is a weak material, and this is our base material, which is basically M4. So the only difference between this model and the previous one is we add an isotropic surface, which has a weaker material, and we change this one to a generalized anisotropic. We hit OK. So this is ready to run. I ran this one before as well. So I just show you, oh, not this one, it's another one. I will show you the results of the anisotropic model. So the slip surface is kind of at the same location if you want to compare. This is the isotropic one. So it's kind of at the same location. Factor of safety changes from 1.32 to 1.3. So a little bit of change, and that's because of the shape of this anisotropic surface, which is a little bit curved. But if you want to look at the contours and see how this anisotropic affected my results, you can look at this one. This dark blue, our cohesion was 1 for the anisotropic surface. And you can see one corner of this slip surface was touched, basically, with the property coming from the anisotropic surface. That's why the critical slip surface went down. So that's the effect of the anisotropic layer. Now, let's look at the safety map. I'm running out of time. So let's look at the safety map, and you can see that in the safety map, we have a weak region here. This is the weakest region, but we have a weak region on this side as well. So what I can do, I can go to the surface options and change this single surface search to multiple. So use MMO and see what MMO gives us, multimodal optimization. And here is the results of multimodal optimization. So you can see that if you do multimodal, you can find a weaker region because the algorithm is slightly different from the PSO itself. And the multimodal actually found a better one, a better critical slip surface, a weaker region on this side. And let's investigate the reason. The reason is this. So if we look at the contour for this lower factor of safety that multimodal found, you can see most of it is that dark, low cohesion. So that's why multimodal, if we wanted to get that one with the single failure surface that we had here, we had to focus more and define more critical slip surfaces, more slip surfaces option to catch this. But multimodal cut this one as well, and factor of safety went down to 1.24. And if you want to look at the values of the friction cohesion at the base of this most critical slip surface, you can see that the cohesion is, let me find the base cohesion for this location, actually here. Yeah, it's in that dark region. The cohesion is 1. So it follows our anisotropic surface, and multimodal found this one, which is better. So that's a unique feature that we added to slide 3, and give it a try. Okay, I think all the questions are answered. Um, there are a couple of questions. What software do you use for create 3D geology modeling surface for slide 3? As I mentioned, any I don't mention the name of the software packages, but any software that gives you triangulated surface can be used and imported to the slide 3 software. Yeah, I think all the questions are answered. If you have any other questions, any requests, you can email me my first name dot my family name sina.javankoshtel@rocscience.com, and I would be happy to answer your questions. Thanks for attending this seminar. Hope to see you in our next seminar, which is gonna be our webinar, which is gonna be 2D and 3D LEM modeling. And enjoy the rest of the day and night, depends on wherever you are in the world.